In this video, we'll discuss the full architecture of transformers, including details of the encoder and of the decoder. Let's dive right in. The transformer, encoder, and decoder architecture. One very central component of transformers is self-attention. And when we discuss self-attention, you might have noticed one detail, namely that unlike for recurrent neural networks, self-attention itself does not actually consider the order of the inputs at all. So when you compute the attention weights for a particular position of your input, then you just look at the query for this particular input and you compare it to the keys of all the other inputs. And it doesn't matter whether the other inputs actually come from the beginning of a sentence, come from the end of a sentence, come from right next to the current input, or actually are the current input themselves. It doesn't matter. All that matters is how similar is the current query to these other keys. Now, for some applications, it can actually be desirable to not take into account the sequence information. For example, if you don't actually have sequence input, but you have a set valued input, then you very much want to treat this as a set. And there it is useful to completely discard the order of your inputs. But for many tasks where we actually do have a sequence as an input, the sequence information is very important. For example, in machine translation, it is important in which order the words in the input sentence are presented. In language modeling, where you try to predict the next word, it is very important in which order the prefix of a sentence is presented. In protein folding, such as in AlphaFold, which uses transformers, you have sequence information. And in RNA folding, which my group actually uses transformers for, we have sequence information. And so in all these different cases, it's very important to actually somehow tell the transformer about the sequence information. And this doesn't happen in self-attention itself, but it happens outside. And the way this is done in transformers is through the use of so-called positional encodings. Positional encodings work as follows. So for each input position, you simply have a fixed encoding of that position. And that fixed encoding is then added to the usual learnable input embedding. So the input embedding says for each word, you have an embedding vector that is learned for this word. And on top of that, you then add this positional encoding to obtain this embedding that now also has a time signal. And you do this for each of your words in the input sequence. So for this one, you have this learned embedding, and you have this different positional encoding that says this is position 2 in order to get this embedding with a time signal 2. And you also do this for the last word here. This is the learned embedding for étudiant. And this then is the same embedding, but now including the positional encoding. This is the word étudiant at position 3 in the sentence. Having discussed the positional encoding, we can now have a look at the transformers encoder block. So we have an input sentence here. Again, a very short input sentence of 2 words. And we have the embeddings of the individual words. Then we add this positional encoding here to each of the words, position 1 and position 2. And we feed the resulting embeddings with time information into the first self-attention layer. Notice that there are also these skip connections here that go around the self-attention. and this happens for each of the words. And so these are skip connections, very much like in ResNets. And also like in ResNets, they're followed by a normalization. Here it's not batch norm, but it's layer norm. And this is the case because, well, we don't actually have large batches. We have a single input sentence. So there's only, in a sense, a single input. And we can't normalize across the elements of a batch. So we normalize across the layer. And so because of these residual connections, skip connections, each of the layers only needs to learn residual changes of the individual words representations. So what happens after this self-attention and its skip connection is the position-wise feed-forward layers and their skip connection. And in contrast to the self-attention, which actually tackles all of the inputs at once, each of the feed-forward layers actually only works on the embedding of an individual word. And one detail here, the feed-forward layers, well, they have weights, of course, and these weights are shared across all the different positions. So there is only one set of weights that is applied to each of the individual positions, and that makes this part of the transformer very invariant to the sequence length. So if you have longer sentences, it doesn't matter. You just use exactly the same feed-forward matrix for longer parts of the sentence. One detail that I already mentioned briefly is that this layer norm, well, that happens after the residual connection. So you can compute this as taking the embedding before the self-attention and the embedding after the self-attention. You add them up, and then you apply layer norm. And that yields the new embedding that goes into the feed-forward connections. And likewise, the same happens in this add and normalize layer. Now, we just looked at the transformer's encoder architecture. So that's over here, we have one of these encoder blocks. And well, we have many of these encoder blocks. In the original paper, there were 6. In this visualization, there's just these 2 here. And the output of the final encoder block, that actually now is also used in the decoder, in the one element that is actually new in the decoder, and these are these encoder-decoder attention layers. So just like in the encoder, we have a self-attention, we have add and normalize, then we have the encoder-decoder, add and normalize. So we also have residual connections around this. Then we have the feed-forward layers, and again, add and normalize around this. So this part here is new compared to the encoder, which is this encoder-decoder attention and the residual connection around it. And this encoder-decoder attention, this is very much the same as we saw before when we looked at attention in the context of RNNs. And so here we've only expanded a single decoder block, and there can also be multiple decoder blocks. And again, in the original paper, there are 6 of these decoder blocks. In the very end, this is followed by a linear layer and then a softmax layer. And the softmax gives you then the probabilities over the output vocabulary. Some details about the decoder. So this decoder is a so-called conditional model. That means it takes a prefix of an output sentence as its input here. So prefix such as I am, and then it predicts the next word. So it would predict hopefully A, and then a student. for this prefix of the output sentence, it computes embeddings, just like is done in the encoder. It also computes a positional embedding, just as is done in the encoder, and then feeds the resulting information into the first self-attention layer. Then, after the self-attention layer, there is this encoder-decoder attention, which looks at the keys and the values of the last encoder stage. And then in the end, there is this linear layer in the softmax. And hopefully out comes the word A. Now, how does this conditional model get started? Well, it just begins with a start token. And it stops decoding when it generates a so-called end token as an output. So it would just get the start token, generate I, use I as an input, generate am, use IM as an input, generate A, use IMA as an input, generate student, then use I am a student as input and output end. And then it would stop decoding. In this self-attention layer, it is actually only allowed to attend to earlier positions in the output sequence. So we have a conditional model. We can't condition on the future. We have to predict the next word. So we can't have information about future words already affect our current judgment. And so in order to enforce that this doesn't happen, what the decoders do in their self-attention layer is to mask future positions. So if you compute the self-attention for I here, so for this first position in the self-attention, then you can't have these connections here from the future. Those are forbidden. And the way that these are forbidden is that just before computing the softmax, you actually set them to -infinity, such that the weight is only shared across all the positions up to the current position I. So in contrast, when you look at the softmax for the second position, then it's perfectly fine to also attend to the first position. It's just not okay to attend to positions in the future. And this brings us to the end of this lecture. And as always, I'd like to leave you with some questions for you to activate the material. I'll see you in the next video. Thank you.